It represents an aggregation already of dark matter, because we think that the dark matter particle probably has a mass of few GeV, and the particles that are the particle size in the simulations I'm going to show you are at about 10 to the 10 times the mass of the sun. Very disparate scale. Okay, so there's that disconnect as well. There's another further embedding of aggregates, okay, that happens. So at the moment, the current maximum is of 10 billion particles, is the Orpheus simulation at the moment. I mean, as an Orpheus is the largest box, most representative of the universe, it's called the Millennium simulation, and I'll show you what it looks like. It's just really, really beautiful. And so you start out, you distribute these density fluctuations. Again, I'll show you visually how it looks. And you basically let it run, and then you compare. So what you do is you compare the statistics of the distribution that you see in the dark matter with that of the observed statistics of the galaxy distribution, modulo a relationship you have to assume between mass and light. Okay, so you start with an initial fluctuation spectrum, you follow the spatial temporal evolution under gravity, you look at the statistics, you make an ansatz, and this is where a lot of so this is called, cosmologists refer to this complicated thing as gastrophysics. So it's like all gas physics, it's microphysics that we don't quite understand on these scales, but we just model them, blindly. Actually, we know we are modeling them blindly. It's not that bad. But then, we make comparisons, and then we say, this is what we've done, and that's why we have. And at the end of this, we say, hey, we have a standard paradigm, and we have a very successful paradigm. But you can see it's pretty problematic. A lot of the steps in between are quite wrong. So this is an example of. So these are the initial conditions of a simulation. So this is from a simulation from one of my students. So this shows you when the universe is about 1.6 gigayears. So I've set up these fluctuations. What you're seeing here is arrows are sort of the flows, the velocity flows as a result of calculating gravitational forces between these initial fluctuations, right? So notice you can sort of pick out these flows, and these are time slices. So there's just 3 different time slices that show you what I have done here is I have taken out, I'm focusing on, I've made 3 separate slices from the full simulation where I've isolated fluctuations on different scales, just to give you an idea. So what really happens is all these things happen at the same time. But I've parsed them out so that you could see that fluctuations really happen on all scales. There's a lot of power on small scales. There's a lot of fluctuations on small scales. There's less on intermediate scales. There's very little on very large scales. However, in the universe, all of these happen simultaneously. But because it's a simulation, I can pick and choose, and I can show you, I can break them up and show you. And what you see as time goes on, so this is about 5, when the universe is 5 gigayears old, and when the universe today is about 13 gigayears old. So what this is, these are dark matter structures, and because I started out with the same initial conditions, and these correspond to slightly different fluctuations, note that the final state is very similar. Looks visually similar, statistically they are not. Okay, you can discriminate between this, this, and this. However, what happens in the real universe is actually a combination of these. I'm just illustrating. So you would form the same bound structures. So when I say bound, these structures have separated out from the expansion of the universe. They're held by their own gravity. Those are these dark blobs that you see here. See that by and large, the most massive, the darkest blobs, you kind of reproduce on every scale. But the features, the larger features are actually quite different. And so in fact, you need to do a full simulation and analyze what you end up seeing is the combination of the growth of fluctuation.
So which law of evolution for gravity, what do you use?
Just the Poisson equation.
Just Poisson equation.
Nothing else. So I'd like the lights turned off because these are just beautiful. Can we darken the room somehow a little bit? Can anyone see this? So this is a slice from the Millennium simulation. And what this is, so this is a region that is 125 megaparsecs. So megaparsecs is about 10 to the 24 centimeters. Okay, so this is a pretty huge region. Okay, so the Milky Way would be a tiny speck here. So this is a beautiful, beautiful slice of dark matter. This is dark matter only. But sorry, we always mock up things to look like light. Okay, so the coloring is always looks yellow, or it's starlight or whatever. And this is one relationship, assumed relationship between mass and light. Okay, there are many possible ones. One of them. So this is the corresponding dark matter map. This is the light map. So notice that the most massive, so this everything here is mass. So the yellowest bits are highest mass, right? So this is the highest mass region, there's a lot of light. So there is a correlation, but that's been assumed, right? And so that's what you see. So you see some bright galaxies here. This is what is done in these simulations to match them to observations. You make an assumption. What you have is you start out with a slice where you have all these fluctuations on different scales. You get a map, a slice that looks like this. And then you say, aha, but how do I compare them to galaxies? I make an assumption of how light and mass are related. I produce a map. I produce a light map. Then I do the same statistics on my data and on this map. And if they match, of course they're going to match. Why? Because there's freedom in how I get this from this. Okay? And so this is a zoom in of this region. Okay? It's a zoom in of this region. And what you end up seeing is, visually you see right away that dark matter is actually quite clumpy. All these pieces are lots of lumps in the dark matter. And they correspond, so here red and blue correspond to galaxies which have old stellar populations, old stars that are red, new stars that are blue. So there's a prescription, lots of assumptions, lots of gastrophysics to go from here to here. Okay? And I think those are very, very problematic. They're very motivated. They're not crazy, but when you say we have the right model and we are very confident, you have to understand that actually there's a lot of freedom here. And there's so much freedom that every time a new technology is developed to see either in the far infrared or the mid-infrared into longer and longer wavelengths, sensitive to longer and longer and redder wavelengths, you uncover new populations of galaxies. Then what do you say? The galaxies that glow in the infrared, they have a different relationship between mass and light. The galaxies that you detect in blue light have a different relationship. So, it's very, very problematic how the level of freedom there is and the confidence in the model. And I think what is disturbing is not so much people saying, well, I think this model works, is the fact that by construction, this model works. And how you would come up with a viable alternative theory is very difficult to see. And in fact, there isn't one. And I think there isn't one not because this is true. There isn't one because epistemologically it's impossible to see how to construct a theory given the way in which we compare with observations. Okay? Again, this is just a zoom in of the light and the mass. Okay, and just to show you, quickly that these fluctuations develop. I remember I passed them out and now it's all fluctuations on all scales. So this is when the universe was about 0.2 gigayears old. Notice that the fluctuations, you see a lot of them. You see that they're becoming more coherent when the universe is about 1 gigayear old, for example. You can already start seeing the regions where your future galaxies are likely to form, modulo that assumption you make. So anyway, at this point, so should fit it to the full screen. So this talk would, these movies are so tantalizing and so beautiful that, if I don't show you this, this is what I'm talking about. So this is from a colleague of mine, Jörg Diamant, who works in Zurich. So this is a simulation, it's all dark matter particles, as I said. There's no light here, right? It's all mocked up to look like light. It's all dark matter, and this shows the assembly of a cluster of galaxies. So those are the most massive objects in the universe. They're going to be relevant because I'll be talking about my work, which really revolves around these kinds of objects. Okay? They're very massive, they're very clumpy, and they might carry a very important signature of the nature of dark matter that is independent of the assumed relationship between mass and light. So that's why these objects are very powerful. So this is a structure, cluster of galaxies. Maybe I'll show it one more time. And what you see are the fluctuations developing, and you can see merging. You can see a lot of violent merging. These blobs are merging with each other and aggregating under gravity. So this is a small patch. Okay, I've zoomed into a small patch from that big slice that I showed you.